Welcome to Educator.com. In today's lesson, we're going to apply what we've learned with matrices so far in order to solve systems of equations using matrices. Okay, first, a system of equations can be written as a single matrix equation, and that is the first step to solving the system of equations. So let's use an example here. Now, recall that in previous lessons, we talked about a lot of other methods to solve equations, such as substitution, elimination, and it depends on the situation which is the easiest method, but this gives you another option, and it can be the best method in certain situations. So first, you're going to write one matrix using the coefficients of x and the coefficients of y, and I'm going to call that matrix x. In the first column, I'm going to call it A. That is the matrix A. And the first column is coefficients of x. In the second column, I'm going to have coefficients of y. Okay, that's the first matrix. The second matrix I'll call B. And for this matrix, you're going to use the constants that are on the right side of the equation, 1 and 3. Finally, you're going to write a third matrix that I'll call x, and that is going to consist of the variables in the system of equations. Okay, so now I have these three matrices, but I want to write them as an equation. And how I could write these is that I could say that A, matrix A times matrix X equals matrix B. And let's look at Y. Okay, so if I have matrix A, that is 5, 6, 4, 3 for the elements, times matrix X, that's my variables, it's going to give me my constants. Well, let's just look at what this is saying by using matrix multiplication. Okay, so this is my matrix equation for this system of equations. I've written this matrix equation right here. All right, let's multiply this out and see what happens. Well, with matrix multiplication, I'm going to multiply this first row times the column. I only have one column, and it's going to give me, for my product matrix, 5x plus 4y. I can't go any farther. Okay. Now, for this second row, I'm going to also multiply it by the column, and then that's going to be 6x plus 3y equals, recall the definitions of equal matrices. Equal matrices have corresponding elements that are equal. So that with this element here, row 1, column 1, and this element here, row 2, column 2, correspond to row 1, column 1, row 2, column 1, row 2, column 1, here and here. Okay, so that gives me 5x plus 4y equals, I look at the corresponding element, row 1, column 1. Here, I look at row 2, column 1, and my corresponding element here, and I get my original equations back. So that shows that this system of equations is equivalent to this matrix equation. And that's what allows us to write the system of equations as a matrix equation. Okay, now let's talk about solving systems of equations. We found this matrix equation, AX equals B. However, if I want to solve, what I really want to find is I want to isolate X, because recall that X, the matrix X, we defined as containing the variables. And I want to isolate that. The same way as if I'm solving a regular system of equations, I want to isolate the variable. Well, we already talked about how this matrix equation AX equals B can be written for a system of equations. So now let's talk about isolating X. Recall that what we want to do is we want to get rid of the A. So we can do that by multiplying it by its inverse. Thinking for a second about why we're doing that. we're taking it and multiplying it by its multiplicative inverse, matrix inverse, A inverse. Well, think about when we're working with just regular numbers. If I have 3x plus 4, what I'm going to do is multiply 3 by its multiplicative inverse, 1/3. If I have 3x equals 4, and I want to isolate the x, I'm going to divide by 3, or I could say I'm going to multiply by 1/3. So if I multiply 3 by its multiplicative inverse, 1/3, this is going to cancel out. And I'm going to end up with 1. Well, what's going to happen here? Recall that when we talked about identity matrices, we said they function somewhat like the number 1 within the world of matrices. So if I'm multiplying a matrix by its multiplicative inverse, then I'm going to get the identity matrix. The same way when I multiplied a number by its inverse, I got the number 1. So A times A inverse, which we discussed in previous lessons on identity matrices, is the identity matrix. So this is going to give me the identity matrix times X equals A inverse times B. Okay. Now, also recall that if you multiply a matrix by its identity matrix, you get the original matrix back. What that tells me is that if I multiply X by its identity matrix, that's the same as the matrix X. So I can just write this as X equals A to the negative 1 B. Okay, so this is what's important to know, but this shows you how we got there. Now, in the last slide, we talked about writing matrix equation AX equals B. Here, we talked about isolating X. So what you really want to work with is this, where X equals A inverse times B, because that will allow you to solve for this matrix and therefore to solve for the variables in the system of equations. For example, write the system as a matrix equation. So let's first, all this is asking is to write it as a matrix equation. We don't even need to solve. Okay, so I have 2x minus 3y equals negative 7. This is 3x plus 2y equals 8. And we talked earlier about writing a matrix equation AX equals B. And that's going to consist of 3 matrices. The first matrix A is going to have, in the first column, the coefficients of x. In the second column, it's going to have the coefficients of y. Okay, then I'm going to write a second matrix B, which is going to have elements that consist of the constants, negative 7 and 8. Okay, then I'm going to have a third matrix that contains the variable. The next thing to do is to put these together into an equation. So that's going to give me A times B, times X, A times X equals B. Okay, so the matrix equation for this system of equations is shown here. And this is AX equals B. Again, I wasn't asked to solve it, so I've done what I've been asked, which is to write the system as a matrix equation. And we can use that as the basis of solving systems of equations, just as we're going to do in this problem. All right. First thing to do is to write the matrix equation. So I need my 3 matrices. The first one is A. And the coefficient of x is 1, and the other is 2. Coefficients of y are negative 2 and 1. The second matrix, B, contains the constants for elements. And then finally, x, with my variables x and y. Now, from this, I could write ax equals b. And we saw earlier on how in order to solve it, I actually need to rearrange things and do some manipulation and end up with this. Because I really want to solve for the matrix X because it contains the variable. So this is the equation I want. And I have A, B, and X. So what I need is A inverse. Recall from an earlier lesson that A inverse is 1 over the determinant times this matrix. Okay, so all I'm doing right now is finding A inverse, if it exists. So this is AB, which is 1 times 1, minus -2 times 2. And just looking over at this, this is going to be -4. So it's 1 minus -4. So that is not 0. So I'm okay. The determinant does exist. So I'm going to continue. I'm going to switch these two, but they're the same number. So it ends up 1 and 1. Then I'm going to take -2 and reverse its sign. So that's going to be 2. Here, I'm going to take 2 and reverse its sign, because that's C, and I'm going to make it -2. Okay. This is going to give me 1 over 1 minus -4 times this matrix. A inverse is 1 over, this is 1 plus 4, which is going to give me 1/5. Okay, so I don't even have to multiply this out because I'm going to be doing some multiplication over here. So leaving this as it is, now I want to have X equals A inverse times B. So X equals, here's A inverse, 1/5 times this matrix, 1, 2, -2, 1, times B. B is 3, 7. Okay, now I'm going to go ahead and do my matrix multiplication to find the product matrix. So the product matrix would be for row 1, column 1. This is 1, 2 times 3, 7. So 1 times 3 plus 2 times 7 equals 3 plus 14. That's 17. So 17 right here. Now, in row 1, column 2, right here, this is going to be 1. Actually, only having 1 row, so it's just row 2, column 1. That's all I need to find. Row 2, right here is the next position, because I have no other column here. So it's going to be row 2, column 1. That is going to give me -2 times 3 plus 1 times 7. That's -6 plus 7, which is going to give me 1. Okay, so I found that I have X equals 1/5 times 17 over 1, which equals, I'm going to multiply 1/5 by 17, that's 17/5, and multiplying 1/5 by 1, and that's 1/5. Now, the matrix X equals this. Recall that the matrix X also equals XY. So these two are equal, therefore the corresponding elements are equal. So I can say that X equals 17/5 and Y equals 1/5. Okay, it's a little bit complicated, but you just have to take it one step at a time. I was asked to solve this using a matrix equation. I wanted to find this equation because then I would have the matrix with the variables in it isolated. I started out by writing 3 matrices, one containing the X and Y coefficients, one containing the constants, and one containing the variables. Then I needed to find, I had A, but I need to find A inverse, and I used my formula to find that, went through and found that this is A inverse. With that, I could then insert it into this formula. A inverse, right here, times B. So I went ahead and I did matrix multiplication to find that I got this matrix as the product, and then multiplied it by 1/5, which I still had out here, to get the matrix X equals 17/5 and 1/5, which equals X and Y. So that's my solution to this system of equations. Okay, example 3. Again, solve using a matrix equation. So I'm going to go ahead and find my 3 matrices that I'll need to have, because I eventually want to end up with X equals A inverse times B. So A is a matrix with coefficients of X, 3 and -1, and coefficients of Y, 7 and -2. Matrix B has elements that are the constants, 4 and 3, and then matrix X has the variables. Okay. Next thing is I don't need A, I need A inverse. And I'm going to recall my formula that this equals 1 over the determinant, AD minus BC, times this matrix. Okay. So A inverse is 1 over the determinant, which is 3 times -2 minus 7 times -1 times this matrix. A and D switch positions, so it's going to be -2, 3. B reverses its sign, and C reverses its sign. Okay, proceeding to find the determinant. 3 times -2, that's -6, that's minus -7. Okay, which is times this matrix. So that's going to give me A inverse is 1 over, well, this is -6 minus -7 or -6 plus 7. So that's just 1. Okay, I have A inverse. I found A, B, and C matrices. Now I have A inverse. And this is what I want. I want that X equals A inverse times B. So I'm going to write A inverse up here, and I'm just going to write this as 1, because it's 1 over 1, times B. B is right here. Doing some matrix multiplication. Row 1, column 1 is going to be -2 times 4 plus 7 times 3. That's going to be -8. Okay. Let me see. This should actually be -7. Okay, so this is going to be -2 times 4, and this is going to be 3, -7 times 3. So row 1, column 1, -2 times 4, -7 times 3. That's going to give me -8 minus 21, which is going to be -29 for row 1, column 1. Okay. Row 2, column 1. Row 2 here, column 1 here. That is going to be 1 times 4 plus 3 times 3 equals 4 plus 9 equals 13. So it's actually -29. Okay. So row 1, column 1 gave me -29. Row 2, column 1 gave me 13. So X equals 1 times this. Well, that's just going to, since this is just 1, I'm going to end up with X equals -29, 13 as elements. And I also know that X is this. So corresponding elements in equal matrices are equal. So -29 equals X, and 13 equals Y. So this is my solution to the system of equations using matrices. Okay, again, solve using a matrix equation. And I'm going to keep in mind that I want to find X equals A inverse times B, where A is a matrix with the coefficients of X and the coefficients of Y. B is a matrix containing the constants, 8 and 9, and X is a matrix containing variables, the variables in the system of equations. I need A inverse. A inverse is 1 over the determinant of A, AD minus BC, times the matrix D, negative B, negative C, A. Therefore, A inverse is 4 times negative 6 minus negative 3 times 8 times this matrix, reversing A and D. So I take A, I put it in the D position, D goes in the A position. For B, I'm going to reverse the sign. I'm going to make it 3. For C, I'm going to reverse the sign, and that's negative 8. Okay, here I have 4 times negative 6, that's negative 24, minus negative 3 times 8, that's negative 24. And you can probably already see what the issue is. That A inverse would equal 1 over negative 24 minus negative 24 times this matrix. And we've got a problem. Because taking this one step further, this gives me 1 over 0. And it really doesn't matter what this matrix is over here because this is undefined. A inverse does not exist. I cannot use this method. So the situation is that there's no unique solution. There may be no solution at all. There may be an infinite number of solutions, but this method only works if there's a unique solution for x and a unique value for y that satisfies the system of equations. So I started out trying to use my method and writing this matrix equation, and I got my matrices okay, but once I got to this step, finding A inverse, then I discovered that the determinant for this matrix A is 0, and in that case, A inverse does not exist. I can't use this method. Okay, that concludes this lesson on solving systems of equations using matrices. Thanks for visiting educator.com.